name is Alon and I am going to present asymmetric image retrieval with cross-model compatible ensembles. Image retrieval is the task of finding an image similar to a provided query image in a large database. Given a query image and a gallery set of images, we aim to find the best match in the gallery. A common image retrieval system is designed as follows. Given a query image, we use an embedding model to encode the image into a query embedding vector, which resides in a multidimensional embedding space. The gallery embeddings were pre-extracted and populate the embedding space. We then calculate which gallery embedding is closest to the query one to find the best match. The majority of existing face recognition and image retrieval methods utilize a symmetric retrieval approach. In a symmetric retrieval setting, the same model is used both for extracting embeddings for the gallery and for the query images. In this setting, there is a clear trade-off between retrieval accuracy and computational resources. Using a larger model almost always achieves higher accuracy. However, it may prohibit use on user-side devices due to limited computational and memory resources. On the other hand, using a lightweight model usually results in inferior representation capability and lower overall retrieval accuracy. Asymmetric retrieval makes a distinction between gallery indexing and querying. Since gallery indexing is a one-time offline process, it can be computed by a large model without being constrained by computational resources. To comply with user-side resource constraint, instead of using the large model for querying, a lightweight model is used. Asymmetric retrieval is not trivial, since embedding spaces of different models are usually incompatible, a problem also known as the cross-model compatibility problem. Previous asymmetric retrieval methods used knowledge distillation-based approaches in order to restrict the query model embedding space to be compatible with that of the gallery model. This method shows significant accuracy improvement compared to methods using only the lightweight query model both for indexing and for querying. However, the accuracy of all these methods is also upper bounded by the gallery model's accuracy and is usually lower than when a large model is used both for indexing and for querying. Another solution for the cross-model compatibility problem is using embedding space transformation. Specifically, it was proposed to transform both the query and the gallery model into a unified embedding space. The embedding space transformation concept can be leveraged to allow higher accuracy than the accuracy of any single model in the system. In order to construct a unified embedding space, two transformation models are trained simultaneously. One to transform the gallery model's embedding space, and the other to transform the query model's embedding space. A similarity and a KL divergence loss are used to constrain both the gallery and the query transformed embeddings to be similar. And a classification loss ensures that the embedding space can be used to classify different identities. We first suggest to modify the unified embedding space scheme. Instead of transforming both embedding spaces into a single space, we transform the gallery model space into the one of the query model. This provides the following benefits. There are no additional parameters added for querying, and more importantly, this allows to transform multiple gallery models embedding spaces into the embedding space of the query model. Ensembles of models have been extensively used in machine learning to boost accuracy. Unfortunately, a straightforward use of ensembles in a symmetric setting might be impractical, since it requires the query image to be inferred by all models in the ensemble. We suggest to incorporate an asymmetric approach, where multiple gallery models embedding spaces are transformed into the one of the query model. This allows lightweight user-side querying and high system accuracy because of robust gallery indexing. These plots show the gains in accuracy as a function of ensemble size. The left plot describes experiments conducted on face recognition and evaluated on the IJBC dataset. The right plot describes experiments conducted on object retrieval using the Stanford Online Product dataset. In all the experiments, the architecture of the gallery model is ResNet 18, which achieves the standalone accuracy shown on the dashed line. Given different versions of gallery models ensembles, shown as different colored curves, we can see an improvement in accuracy as the number of gallery models increases. Additionally, as the combination of gallery models is more diverse and different architectures are used rather than the same one, the accuracy also increases. Next, we introduce a gallery image rejection method that leverages the diversity between multiple transformed embeddings to infer if a given image is easy or hard to match. First, an image is encoded by all gallery models into their corresponding embedding spaces. Then all embeddings are transformed into the single query model embedding space. Finally, we calculate the variance between the embedding distances. Low variance means that the models agree on the place of the image in the embedding space, suggesting that the image is easy to match. On the other hand, if the models do not agree on the place of the image in the embedding space, the variance will be high, suggesting that the image is hard to match. We show the accuracy increase gained by filtering out gallery images for both the IJBC and the SOP dataset. As we decrease the threshold for acceptable variance, more images are rejected and the overall accuracy is increased. In this slide, we show examples of images in the gallery of the Stanford Online Product dataset. The following are the 50 images in the gallery with lowest embedding distance variance. These are images with just a single object that are easy to be recognized. On the other hand, the 50 images with the highest variance are hard to recognize. Some images suffer from extreme zoom or partial view of the object. Some have multiple objects in the image, and some are non-natural images as sketches or 3D renderings. We also provide a few examples of IJBC gallery images with different uncertainty levels. Gallery images with low uncertainty levels generally contain faces that are clearly visible, as opposed to images with high uncertainty, that often contain occluded or extremely rotated faces. Additionally, it can be observed that for a medium level of uncertainty, a large proportion of faces wear glasses. Thank you.